Okay, so we're gonna do 2 sample confidence intervals today. So we're gonna go through how to do it, reading our formulas, put them in right, and we're gonna do 3 examples. So I'm gonna do a couple, and then our last one's gonna be like a little different. We'll do it a little differently. Okay, so we're not gonna actually count the chocolate chips. I've done it before. It's like, name brand versus like Walmart brand type cookie. And obviously, the name brand ends up, at least when we did it in the past, they have more chocolate chunks. That makes sense. That's good. You're actually paying for better product. But okay, so let me just give you some information. Let's say that in a chocolate chip cookie, I'm finding, let's say I found an average of 21.56 chocolate chip chunks. That's a lot, yeah. There is a lot in them. They're just tiny little things. They're in there. And then let's say we did a sample size for both of these of 28. So sample size 28. Okay, and let's say this one has a standard deviation of 2.4849. Just going off what I did. 49. What was this number? 6? Jeez. Okay. And then let's say that the less known brand, whatever, had 18.22 chocolate chips with the standard deviation 4.51. Okay. So what we're going to do is do a confidence interval for the mean difference in the number of chocolate chips in one cookie from Chips Ahoy versus Meyer, Chipsters, whatever. So we're going to see who does more. Okay. So what we're going to do is, so we can do this one. So what's the difference between the two? And so on the difference, you can do it either way. Like you can do Chips Ahoy versus Chipsters, or you can do Chipsters versus Chips Ahoy. It's just you'll get either a positive or a negative, but either way you're going to get the same conclusion. So the difference, let's make sure.
Teachers, quick all call, please release all the students in the email that Mr. Boobin sent out at this time. If you have not already, please check the roster carefully and send all students to the auditorium, the blue auditorium at this time.
You gotta go to the auditorium.
I got it.
Yeah, you gotta go to the large auditorium real quick. It won't be, yeah. You just, they have like a list somewhere, so.
Okay.
Yeah. Okay, so just make sure to list like the Ahoy minus Chipsters. Like that's what I'm doing. You could do Chipsters minus Ahoy, but that's what I'm gonna do. So what's the difference between them? So 21 minus 18. Yeah, it's like 3 something, right? 3.4. Yeah. Okay, so that's our difference. Okay. So so when I first introduce something, I think I should do the conditions every time, but I want to skip over these to actually get straight into the math part, because the conditions are the same every time. So we'll do them on the next problem, but I want you to see the connection straight to the math here. So let's construct a 95% confidence interval for the difference in the mean number of chocolate chips in Chips Ahoy versus Chipsters. Okay, so for our thing, how about I write what we did yesterday? So for a one sample, we did this. We did the mean plus or minus the t-value times standard error. And the formula sheet oops. So if I go over the formula sheet, says the standard error was S over the square root of N. So that was yesterday what we did for one sample. So it's like this, S over the square root of N. Alright, so for two samples, this is what we're going to do today. So this one, the X bar is the difference between the two. So like we did X bar 1 minus X bar 2, which we just got is like 3.34. Plus or minus, the T still goes there. And then you're still doing times the standard error. And so look on the formula sheet nearby. And if you just know how to read, what's up? Oh, okay. So if you can identify where it's at on the formula sheet, so you go to the back side, we're on our means, we've got 2. This is the formula we're going to use right there. So just identifying what section we're in, standard error. So I'm going to use this formula. So it goes like this. It says square root S squared over N. So S1 squared over sample size, S2 squared over sample size 2. So we're like adding our standard deviations together. So this is the formula for combining those two standard deviations together. Okay. So that's what I'm going to do. I'm going to plug in to what I have. So we said that the difference, 21 minus 18, was 3.34. Plus and minus. And then let me do the S's here first, and then we'll look at the T. So standard deviation of the first one was, I said that it was 2.49. So I'm going to square it over the sample size was 28 for both. So I'm going to do 28 plus the number I gave for standard deviation for the chipsters, 4.51 squared over sample size 28. All right. And then the T, so to get your T value, remember we need to get our degrees of freedom. And it's also dealing with the 95% confidence. So here's the tricky thing on the degrees of freedom for the sample size. So since this one, both our sample sizes were 28, it actually makes it simple. So like both of them are 28. So the degrees of freedom is 28 minus 1. So you can use the degrees of freedom of 27. On the back side, on the next problem, we're going to do like what happens if our sample sizes are different. But in this case, our sample size was 28, so we do 28 minus 1. So I'm going to look up on our table, degrees of freedom, 27. So I'm going to go all the way to the T table. Degrees of freedom, 95% confident. Degrees of freedom, what was it, 27? 2.052, I think. So that's my T, so giving it. Okay. So since you have a paper copy of these, if you need to like write yourself a big note that this section over here needs to be n minus 1, like do it. Like don't make the mistake of doing just n. So it's always n minus 1 over there. Okay. What did I say? 2.052. So again, it's all the same bones and ideas. It's just like, can we read our formulas and know which one to plug in where? But it's all the same ideas kind of flowing down, just being able to plug in stuff correctly. So I'm gonna put this in the calculator. So kind of big and complicated. Alright, I got 1, so let's see, my rounding here. So I'm gonna round to 2 decimals, and my thing here is 1.9977. So like, to round up, that would become 0, 0. So that this becomes 2, like a nice 2 number there, for our margin of error. So it becomes 3.34 plus or minus 2. So then, plus or minus 2, that's 1. So I got, let me finish this off on the next page here. So plus or minus 2 from 3.34 gives me this range, 1.34 to 5.34. Okay, so that's my interval. I am 95% confident that this is the true average difference between Chips Ahoy and Chipsters. So what this means is, let's look at number 6. Do we have convincing evidence that there's a difference in the average numbers of Chips Ahoy and Chipsters? So does this show convincing evidence? Yes or no? So, in this case, both of these mean, so since we did, remember I did Chips Ahoy minus the Meyer, and so if I would have done it the opposite way, both these numbers would have been negative. It would have been -5 to -1. So both of these numbers indicate that Chips Ahoy is greater than Meyer. So do we have evidence? I would say yes, we have convincing evidence. Like, we believe that somewhere on this positive number is the true difference. So Chips Ahoy is winning by somewhere between 1 and 5.
So what would that sentence look like?
So, like on number 6, you could say something like this, like, yes, because our interval indicates Chips Ahoy, so I'll just say Ahoy is greater than Meyer by 1.34 to 5.34 chocolate chips. Chocolate, beautiful, things like that to learn how to spell, since I don't know how to. So, I don't know, is that even how to spell
No.
Oops.
You added another O.
Yeah, I see that now. That's okay. It's okay.
Chocolate.
Slightly challenged over here.
Wait, so do you have to include the 95% in our sentence?
You could.
No, but like, do we have to?
We probably should.
Be like, I'm 95% sure that.
I'm acceptable.
Okay. So remember, when you're doing a difference, so let me just write something, right? So if we're doing a difference, if my interval, like in this case, I had positive to positive, this means Ahoy is greater. If I had negative to negative, that would mean Ahoy is less than Meyer. And if I had negative to positive, that means no evidence. Because like this means ahoy less than, this means ahoy greater than. So remember on two sample stuff, if you've got this negative positive overlap, know that that means it really doesn't tell us anything. Kind of the evidence there. Alright. Cool. Okay. Alright, so I'm just gonna try and do some more problems, just to get us some more stuff. Alright, so on the back side, we got our check. And what I'm gonna do here is I'm gonna do your conditions with you, and then I want you to actually do the math of it. But we're gonna be good statisticians, and we're gonna do our conditions this time.
Dang.
You know you can major in statistics, they have like a pretty good stats program. They do?
No.
And then their thing is like, they say that you go out of college with like 70,000 salary or something like that. Stats
And
people
then-
making money. And, oh well.
Why don't you have some, like,
Huh?
why don't you have a job like that?
I don't know. That's okay. You know. I'm not in it for the money.
Yeah.
Wow. Passion of teaching. Oh, what am I doing? Okay. So on the conditions, maybe I need to go to the actual problem here. So,
Yeah, figure out if it is.
so what's happening here is people ages 15 to 19, how much they read in a day, versus people ages 75 and over, average time they read. And so when you're doing your conditions, you need to do it for both groups. So what I'm gonna do is I'm gonna write 15 to 19, and then I'm gonna say like 75 plus. And like, it says in the paragraph that they did a random sample of both of those. It said, where does it say? It says it somewhere. Uh-oh. Oh, there we go. Random samples of 975 and 1,000. And so when I'm doing my conditions, just make sure you're checking the box for both. So yeah, and then the other condition is 975 less than 10% of all 15 to 19-year-olds. And that's true, there's more than 9,000 in that category. And then is 10,050 less than 10% of that population, which is another check, so we're good. And then, okay, is our distribution normal? So the way you calculate, the way you do that is your population normal? Is the sample size bigger than 30, or is the sample data not skewed? So in this case,
Bigger than 30.
yeah, in this case, if you have that, then you're good. Just say, and 975 bigger than 30, 10,050 greater than 30. So that's for your normal. Do you have a normal distribution? So if you have a really big sample size, then it doesn't matter. Like then you can just say, yes, I know it's going to be normal. Alright, so what I want you to do is I want you to try and do the math part of it on your own here. See what you can do. I'm going to go through it with you. So I'll give you a few minutes. I want you to do just what we did on the front side. So I want you to do the whole formula, go through it all, get the T. And I want you to try, purposely, so the T star might be where you screw up here. I just want you to try and get your T, and I'll explain. So just try it out.
Okay, I think I know how to.
Just, and then I'll explain once you've done it. Okay, so at this point you're attempting through, you're kind of getting your own thoughts in. Let me kind of go through and see. So what I wrote out was I just did 15 minus 75. You can do it the other way. We're gonna get the same answer, just yours will be positive, mine will be negative. It doesn't matter. You can do it that way. So I'm just getting this information from the paragraph. 7.8, standard deviation 5.4, 43.8, standard deviation 35. Let me plug all that in. So I'll do that for over here too. So it was, so 5.4 over 975 plus 35.5 over 1050. Okay, so that's like our bones. Again, if you did 75-year-olds first because you want to work in a positive number, that's totally fine. Okay, on the T here, so the T has to go with like, I'll work it over here. You have to do with degrees of freedom and how confident you are. So what was our confidence? 95% confident. But how do we get our degrees of freedom? So we did a sample size, 975, sample size 10,050. And so what we're going to do is we always want to go on the conservative side for our statistics. And so what we're going to do is you always take the smaller sample. So if you have two different sample sizes, what I want you to do is every time go for the smaller one, and then we're going to work off that. So like the degrees of freedom is going to be 974. And then even that gets a little weird on
Yeah,
the...
it goes down to 100.
Yeah. So, but we're always going to go conservative. So, you know, we live in Texas. Like, that's where we're going to go. So, 95%. So then, yeah, like over here, you've got 100 and 1,000. And even though we were like so close to 1,000, we're going to go all the way down to 100. So we're always going to round down over here. So even if you're literally one thing away from the other one. So we're not going to use the 1,000, we're going to use the 100 one, and it would be 1.984 is going to be our T.
Are there tables that have like the 500 in there, or like a...
This table for the test is not, it doesn't have it. If
Alright.
you use the calculator can get you a little bit more accurate one. But I've gone away from doing stuff on the calculator because when y'all do it by hand, you understand it a little more, even if it takes a little bit more work. So 9.84, so that's going to be my, oh wait, that's not right, 1.984, right?
Yeah.
Okay. Like 9.84 is huge. Okay. So always just gonna go round down, use the smaller one, like all this stuff, just think, don't go too high is the thing. So always go down. Sure. Alright. So when I do this, what did I get? So when I do 1.984, whoa. Okay, so when I get that, I'm getting 2.200. So just 2.2. There's a good one there. And then 7.8 minus 43.8 is negative 36, plus and minus 2.2. So if you did it the other way, at this point, you should have positive 36 plus or minus 2.2. You still get 2.2. It doesn't matter. So then when you do that, so you get somewhere like the lowest value is negative 38.2, or is it 38.8? 38.2, yeah, and then negative 33.8, I think is the closest one to 0, the biggest one. And if you did it the positive way, you should get positive 33.8 to positive 38.2. Either way, you're getting the same numbers. And so then, like, what's the interpretation? So what we're doing is, this is the read time for teenagers versus the reading time for older people. So this means somewhere in this range is the actual difference in read, like the average read time a day. So I can say older people read this much more than younger people per day. So that's what I'm going to say. I'm going to say, I am, for Alethea, 95% confident. And then I can say it like this. I can say, I'm going to switch mine over to positive numbers, or you can leave it as negative. But I'm going to say I am 95% confident that 75 plus read on average, and then it was 33.8 to 38.2 minutes more than 15 to 19-year-olds. So you could have written that differently. You could go a different way. You could go, I'm 95% confident that the true difference in 15, 19-year-olds to 75-year-olds is negative 30.8 to 38, negative 38.2. Or, like, I just kind of made it into, if I'm actually speaking, I wouldn't have said negative. I would have just said older people read more than younger people. So just putting it into context of what's going on. But so they're reading about half an hour more than younger people. I don't know if that, it is leisure reading, so it's not forced reading, because, you know, y'all might be forced to read just enough as much. Okay, so that's kind of that little problem. So setting it up, getting our little conclusion, doing our interval. So we've got all our things. Again, kind of the thing on that one was, I've got my nuts and bolts, but then the T, so to do the T there, always go for the lesser value. And then that means on the table, we went all the way down to 100. So make sure, just getting that. All this stuff, like the T is on the formula sheet, this formula is on the formula sheet, so like we can just get down those where they all are and understanding it should be good. Okay, let's do one more that's slightly different. So let's do this other page where it talks about, it says memory training at the top, but I'm going to do the backside, check your understanding. So I'm just going to go straight for the problem already given to us on the back. So on the other notes page, check your understanding. Okay. So what's going on here is how much time are teens spending online? So do parents realize how much time they're spending online? So they did a study. So what they did is they did a random sample. Here's all 10. So they did a random sample of 10 teenagers. And you can see they listed them all out. Each teenager was given a Chromebook, free internet for 6 months. During this time, the internet usage was measured in hours a day. And what they did at the end is they asked the parents to see what they thought the amount of hours they spent a day. So this row here is the actual number spent on the computer or on the internet. And this row here is what the parents were guessing. Like, oh, I thought my kids spent 3 hours a day, when they actually spent 4.7 hours a day on the computer. So this is a column, or an experiment on like the same person, but like, or on the same thing, but like the actual versus the perception. So it's actually, what this is this is something called a matched pair experiment, because it's actually like the same. It's kind of hard to identify sometimes, but whenever I'm doing, like, let's say I gave y'all the AP test right now, and then I put you through a month of review, and then I gave you the AP test, and I compared the two scores. That would be matched pairs. I'm comparing you versus you. So when you're doing that, that's a matched pairs. So this is like comparing what we thought versus what actually happened. But it's the same kid. Like, the experiment is on the same kid for both of these. The same kid for both of those. So that's matched pair, when it's the same thing or person being experimented on. It doesn't have to be a person. It could be Reagan's flowers or something like that. Like what they were originally after she poured Coke on them or whatever. Or did she give them Coke? Is it Coke or is it actual drink Coke? No? Okay. Alright, so let's do R.I.P. Reagan. Miss you. Okay. Alright, let's make on A, we don't really have to make a dot plot, but this is just seeing like what's actually happening here in the problem. So let me go for like, I'll even go negative, because we're doing, this is the difference between actually spent on the time and perceived spent on the time. So like,
But it's still positive, because they're all positive numbers.
yeah, so they're all positive numbers, that's what we're gonna see. So like what happens is, here's the row, and they're all, like the dot plot is like all over here. So maybe I won't even put the dots on there. So what does that tell you? What does this dot plot tell us if like all the dots are positive? What's like our initial findings here?
That they underestimate.
Yeah, the parents are underestimating. The actual is bigger than, so yeah, that's a good way of saying it. Like parents, it's telling us parents underestimate. So that's fine. That's just like our initial findings. So what we're gonna do is we're gonna find like the actual, like where we think the actual number is. So that's what's up there. Okay. So what we're gonna do is we're gonna find the mean difference and the standard deviation difference. Okay, so maybe let me go back. So when we're doing a matched pairs, when it's a matched pairs, what we're gonna do is we're gonna do a one sample test for this. Like it's not gonna be two sample. We're just gonna do the test on the difference between the two. So like what we're gonna do is we're gonna get this information in the calculator, and we're just gonna do a one sample test. So like instead of doing the difference between them, I'm gonna get the information for this and do it like a one sample problem. So that's the big difference. If it's matched pairs, you do like a one sample for the difference. So what I'm gonna do is, I'll put this on this calculator so that the recording can see it. is I'm just gonna put it in the calculator and get my X bar and my standard deviation. So I'm gonna make a new document. Okay, make a list. And I'm only gonna make one list, and I'm gonna make it for the difference. So I'm not gonna put the 2 in, I'm just gonna put the difference in. So I'm just gonna do that bottom one. So it's like 3.4, 3.2, 4.7, 4.7, 4.9. Okay, so I'm just gonna make a 1 column for that one difference, and then I'm gonna get so I'm gonna make a calculator. I'm gonna do the menu, statistics, calculation, 1 variable. I'm gonna get the information on that. Which it matches what I did before, so that's great. So 3.02, 1.315, so I'll go 1.32 for my 2 things. So on my mean and standard deviation, I've got 3.02, 1 point, rounded up to 2, 3.2. So for matched pairs, I'm just gonna do it for a 1 sample. So just a 1 sample for the difference. So I'm not actually gonna do the 2 between them. And remember, we got like a sample size of 10 kids there. So for a 1 sample, it looks like this. So those are like my formulas for a 1 sample. So then I'm just gonna plug in, like, the mean difference was 3.02 plus and minus 1.32 over the square root of 10. And then the T, so I've got 90% confidence, degrees of freedom is 9. So I'm gonna look it up on my table. 90% degrees of freedom 9 is 1.833 is what you should find. That's what I just found. So 1.833. So again, the main difference here is like this. This right here is our main difference. I'm just doing it for the 1 sample of the difference because it's a matched pair. So because it's like the same person being experimented on or the same thing. Okay, so you do that. What did I get? I got 0.77. So 3.02 plus and minus is there's my interval. So that's what I'm thinking. Somewhere in that interval is the true difference in like actual spent time versus parent perception spent time. So like parents are underestimating between almost 2.5 to 3.5 hours off. That's pretty big. I could see that though, you know. I feel like our own perception's off. Like if I asked you, what your actual screen time was yesterday and what you thought it was is probably off. That's what I found. That it's actually probably way more than what you guessed. But yeah, so that's like mine. That would be my difference. So the main thing on that one is that it was something called paired data, matched paired. So when I do that, I'm just going to do a one sample for the difference. It's kind of weird, but when the identifier is that it's like the same person being experimented, the same thing, same questions, whatever. Alright, so that's the main difference between the two. Okay, so what I have is make sure, so on Schoology, or you can turn in person, that worksheet from yesterday, so you can work on that. And then I've got a worksheet that has a couple of these questions for y'all to do in class today as well. And then on Friday, I have a golf tournament. It's a half day, so I'll have nothing for you on Friday. So this is like our last day. We'll pick up again after the break. I'll keep going, but that's what I got. So we're gonna work on that. We got